I want to walk you through all the steps for designing a race car suspension. In this episode, we'll design together the pickup points for the actuation systems, rockers and anti-roll bars. Hello everyone, this is Bruno. In this series, I'll walk you through all the process for designing a race car suspension. Today, we're going to design together the pickup points for the actuation systems, such as rocker, springs, and anti-roll bars. Before we start, I want to give a quick recap of what was done so far. So this exercise is a case study where we're designing together the front suspension of a GT3 car. So we are focusing more on the design process and not so much on the values, meaning that all the values used here are only examples. They are not meant to be used as recommendations. Besides that, obviously there are many important parameters that are not considered, since this is just an exercise. Alright, so in previous episodes we have already designed the outer pickup point, as we have discussed in length on video number 2, and we have also designed the inner pickup points, meaning the pickup points on the chassis, on episode number 3. Now that we have all of the inner and outer pickup points defined, it's time for us to attack the actuation pickup points. As you can see, all of the design is documented using these notebooks. Like this, I can show you how to properly document such a project, and also you can get access to all of these notebooks in the video description. Alright, so now when designing the actuation pickup points, these are the pickup points we're going to focus on. So we have the pickup points of the rocker, we also have the coilover pickup point, as well as all the pickup points from the anti-roll bar system. If you remember well, before we start our design, we define our design target. So this table includes what motion ratios we would like to see for our actuation systems. Also, what is the wheel rate variation that we want as the car moves up and down. And the same is valid for the anti-roll bar. So we're going to come back to these parameters once we are designing our suspension system and understand better each of them. So without further ado, let's jump right into OptimumKinematics and start designing our suspension. If you remember, last episode we finished with a V6 with all of the wishbone and tie rod pickup points defined. Now I just created a V7 and I added a actuation system. So here we can see a push rod, we can see the rocker system and its attachment on the chassis that we call pivot axis, as well as the coilover. So here, even before we look at other parameters such as motion ratio variation, let's make sure that all of our pickup points are on the same plane. And as we can see, they are actually not. So this was just an initial draft that I created. I think that by looking at the chassis, the current chassis design, this is a good placement for the system in which I can minimize loads, I can minimize weight. It's good packaging, it's not in the way of other components of the car. However, I just need to make sure that everything is on the same plane. In order to make sure that all the pickup points are on the same plane, you can use, for example, a CAD software. In our case, we're using a simple geometry tool where we can first define the plane of the rocker by defining its 3 pickup points, and one of them being the pivot axis, which must be perpendicular to it. And then after that, we can look at all other pickup points for the push rod, for the rocker, always making sure that they're on the same plane. So throughout this exercise, whenever I make changes, I'm always going back to this tool in order to make sure everything is on the same plane. Okay, now that we have all this bureaucracy out of the way, let's start looking at the kinematic parameters that will define the behavior of the car. The first parameter we should be looking at once we have our initial draft of the actuation system is the motion ratio. As you can find in our documentation page, the motion ratio is nothing more than the displacement of the chassis or wheel compared to the displacement of the damper. So there are 2 different ways in which we can create this definition. One of them is wheel displacement divided by damper displacement, while the second one is damper displacement divided by wheel displacement. In our case here in this exercise, we're always going to use the first definition, wheel divided by damper. Why is the motion ratio important? Because it will define, for the same suspension movement that you get, how much compression you have on your damper. Besides that, it will influence the effective stiffness of the car, of the suspension, called wheel rate. Next, when we define our motion ratio, it will be a main parameter defining also the wheel rate. So as you probably know, the wheel rate is basically the measurement of the stiffness of the suspension as seen on the tire or on the wheel. So in this case, we do have the spring stiffness over here, but it's not the effective stiffness of the system. You have a mechanical conversion over here, and then you can find the wheel rate, meaning when you push the tire, how much displacement you get for the force that you applied. And for vehicle dynamics, this is what matters the most. So the wheel rate is defined as spring stiffness divided by motion ratio squared, based on the definition that we are using. If you change the definition of the motion ratio, this equation will change as well. All right, so now let's get back to Optimum Kinematics, understand what motion ratio we currently have and also what motion ratio we want to achieve. If we look at the quick outputs that Optimum Kinematics gave us, we can see that the motion ratio is about 1.131. This means that we get more or less the same movement on the wheel and then just slightly less on the damper. For this design, we actually defined a motion ratio of 1.35. How did we come up with this number? In our case, we're trying to get a damper that does not have a really long stroke. So we already know more or less how much suspension deflection we want in maximum condition, and therefore we need to minimize how much damper displacement we get. So in our case, we saw that by using 1.35, we're going to be safe and use all the range that we want from the damper. Now we know that we want to go from a motion ratio of 1.1 to a motion ratio of 1.35. How do we do that? Well, it's basically by changing, if we look at the rocker design, we have the rocker pivot axis, we have the push rod pick a point, and we have the damper pick a point. It's all a matter of mechanical gain. So we have to play with this distance as compared to this distance, and then we're going to get the motion ratio we want. So let's go back to our design software and try to play with this distance. As you'll see, I'm going to take a manual approach for the sake of the exercise, but then later on, I'm going to show you how to use optimization to make it a lot more efficient. So we saw that we have two options. Either we increase this distance over here, or we decrease this other one. We're going to start playing with the push rod attachment and try to send it a little more forward. So let's do just a couple millimeters because the motion ratio is extremely sensitive to that. So for that, I'm going to do an X value a little bit forward, which will be, let's say, -4. And then remember that I also need to compensate Y or X in order, or Y and Z to make sure they're on the same plane. For that, I'm going to increase Z slightly. Okay, so we can see that the motion ratio went from 1.1 to 1.2. So it's already halfway to where we want to get the number of 1.35. Let's try now the opposite with the coilover pick a point. In this case, we need to decrease this distance so that for the same rocker rotation, we get a smaller linear displacement on the damper since the arm is a little shorter. Here, we have to change the Y coordinate. So let's make it a little more to the outside of the car. Let's pick 3 millimeters. And then I also need to decrease Z a little bit just to make sure that it's on the same plane. And you should be using a CAD software in order to accomplish and make sure that it's on the plane. All right, so 1.29. So not quite there yet. I'm going to do another round of iteration until we get to something close to 1.35. All right, so we got to 1.347, which is pretty close to the number that we want. And I'm going to be happy with that, considering it's just the first manual iteration. It will be very dangerous if you stop the design here once you achieve the motion ratio that you want. Because motion ratio variation is as important, if not even more important, than the static number for motion ratio, which is what we are getting here. So let's look at how the motion ratio is changing as we compress and extend the suspension. Let's see if we are in a good place. For that, I'm going to run a simulation in which we are compressing and extending the suspension by 35 millimeters. We get the results, and now we're going to display them. And there you go. You can see the crazy amount of motion ratio variation that we get here. So even though static is 1.35, as we would like to have, if we compress the suspension by only 20 millimeters, which will happen at the track, we are already at 1.45. It might seem small, However, remember that the motion ratio squared is influencing the wheel rate. This means that you would heavily change the suspension stiffness at different heights of the car. Besides that, in this case, as we compress the car and we go towards a negative number of heave, the motion ratio is increasing. In our definition, a higher motion ratio will soften the front suspension, which is not great. Why? Because when we're running at low speeds, we're running up higher. At high speed corners, we have more downforce, so the car is running lower. We are softening the front axle, and what does this give us? It gives a more oversteering mechanical balance. You are increasing the grip on the front, and therefore creating more oversteer in high speed corners, which is not something we necessarily want. Unless your car really asks for that, we would be doing actually the opposite. In my designs, I will try to target a car that is slightly more understeer at high speed corners, meaning that I would like a motion ratio variation on the opposite direction. So like as the car compresses, the motion ratio slightly goes down, increases the front axle stiffness, and provides a little bit more mechanical understeer, meaning a more stable car. All right, so we saw that first we need to reverse the direction of motion ratio change. And next, I also want to minimize or to lower this motion ratio variation. How do we do that? So let's go back to our notebooks and understand how can we get a higher or lower motion ratio variation. If we look in this image, we have the case where we have a small motion ratio variation at a given rocker configuration. And then we have another option where we have a larger motion ratio variation with a different rocker configuration. So let's understand the difference between both. Well, for this first rocker configuration where we have again the pivot axis, the connection to the push rod and the connection to the coilover, we have the push rod angle versus the line connecting this pickup point and this pickup point, similar to the angle of the coilover and the line connecting this other pickup point and the pivot axis again. So whenever these angles are similar, we should expect a small motion ratio variation. The other case where we have a larger motion ratio variation, look at what's going on. Even though the angle of the coilover and these two pickup points is still similar to the one before, it is different compared to the angle of the push rod and these two other pickup points. So now we see that here we have an angle close to 90 degrees, meaning that whenever you are rotating the rocker, you have a lot of transfer to a linear movement, while for the push rod pickup point, we have an angle lower than 90 degrees, meaning that whenever the rocker is rotating, the linear movement is not as effective. Well, in the end, the static motion ratio can be the same. So when we go back to our OptimumKinematics project, we need to check these angles. Are they similar? Are they not? In what direction? Is one a little higher than 90 degrees, the other one is slightly lower? How should we play with them to decrease? First, change direction of the variation and also decrease it. So from the top view, we can quickly see how different these angles are. So let's look first at the coilover angle. We can see that the angle is close to 90 degrees when connecting the pivot axis to the coilover. Slightly lower than 90 degrees, maybe 85 to 88, something around that range. But if we go to the angle of the push rod versus the pivot axis, we can see that it's a lot higher than 90 degrees. Do you remember on the second case where we had different angles for these two components, the motion ratio variation was higher? So it is the case here. So I think that our first bet is to try to put them at more similar angles. And then from there, when we have a small variation, we can play with these angles until we have the variation we want in the direction that we want. Okay, so since we see that one of the angles is a lot different than the other, we have to make them similar. In this case, I prefer to change the push rod pickup point in order to have a more similar angle. In this case, we would have to send this pickup point a little bit more inward, and then we should get an angle closer to 90 degrees as well. So let's do that. I have to change this pickup point, and we're gonna be using a number. Let's try to guess an initial number in this manual iteration. 10 millimeters to the inside. I'm gonna correct it on the Z coordinate as well. And we see that the number is getting a little closer to the 90 degrees that we're targeting, or slightly lower than 90 degrees. I'm gonna try a little further, a little bit more, and then we run a simulation to see where we are. So now with the simulation performed, we can compare both of our results. So we had the previous results in blue, while we have the new result in orange. Well, first thing we notice is that the motion ratio changed a little bit. Of course it did. When I'm playing with the pica points, the effective arm length, or the proportion of them, also changed, meaning that we need to iterate until we get to where we want. On the other hand, we see that it happened exactly what we were expecting. The variation changed from a huge variation to a much smaller variation. We can also see that when I am compressing the suspension, the motion ratio is slightly going down, even though it's going up. Whenever you are designing a rocker system, it's normal that you're going to see this sign behave of the motion ratio. In any case, it is going in the direction that we want. I would just like to amplify a little bit more and get a little bit more motion ratio variation for a lower number when I'm compressing the suspension. So I'm going to give it one more try with a manual approach before later we run an optimization. Alright, so now we have our next iteration and I'm getting pretty happy with the results. So again, the static motion ratio is not correct. I'm going to have to fix that by adjusting the arms, just like we did in the first step. However, the variation is getting pretty good. So as we can see here, if I go from 0 to 20 millimeters compression, it is going from 1.395 to 1.38, which seems to be in the range that I would like to see this variation. But let's try to be more data-driven. What is the variation of motion ratio we want and why? How do we determine that? As we discussed previously, I would like the car to have different behavior at different height, meaning at different downforce values and different cornering speed. So instead of purely looking at an arbitrary number, such as the motion ratio, I want you to think in terms of wheel rate, in terms of roll stiff. So my target here will be, as the car goes down 10 or 20 millimeters at a high-speed corner, how much more stiffness I want on my system. So for the sake of this exercise, I'm going to say that as I compress the car by 10 millimeters, or every 10 millimeters that the car goes down, I would like to see a 2% increase in wheel rate. So how do we go from motion ratio to wheel rate? Let me show you a very simple spreadsheet that will help us. So in this case, I defined 3 different levels of heave. 0, which is a low speed corner, let's say static position. 10, which is a medium to high speed. Maybe high speed can be even lower than that, but I want my reference to be 10 millimeters. And I also put the maximum displacement that I expect for our suspension design. So let's say that in this case, we found a motion ratio of 1.395. So we have static 1.395. All right, so what matters for the wheel rate is the motion ratio squared, meaning that the wheel rate variation will be proportional to the motion ratio squared. This means that I don't even need to define a spring stiffness at this point. I just look at motion ratio squared, and I want to see a change of, let's say, in this case, 2% for every 10 millimeters. So in this case, what is the motion ratio we need at 10 millimeters compression in order to get to this 2% variation, which is the number we see over here. So let's try to play with the numbers, and I see that if I get to 1.38, I get the 2% variation every 10 millimeters I want. Now, going back to our analysis, I can see that if I go from 0 to 10 millimeters compression, I am getting to a motion ratio of 1.385. So I actually have less than 2% variation for every 10 millimeters, which could still be acceptable for a race car. Remember, these numbers are just examples. I'm not focused on them. In any case, we see that after that, we will need to iterate in 2 different aspects. Number 1, get back to the baseline static motion ratio we want, 1.35. Number 2, get to the motion ratio variation that I want. In this case, the 2% motion ratio squared every 10 millimeters. This would still require a few more iterations. I'm going to leave it like that for now because in a few minutes, we're going to run an optimization to find everything at the same time. Now that we're happy with the first version of our rocker system, it's time for us to document. Remember how important it is for you to document all of the steps, so later on you understand what decisions you made and why, and what is left for you to do. Okay, so now it's time for us to get back to OptimumKinematics, create a new V8, and add the actuation of the anti-roll bar system so that we can start working on it. So this is the initial draft I created for the anti-roll bar system in V8. As you can see here, I'm connecting the droop link directly to the rocker, even though it could also be connected to the wishbone, for example, or even upright. with a different anti-roll bar configuration, and I'm using what we call a U-bar, which is the most simple or the simplest anti-roll bar that we could use. In the case of the anti-roll bar, I cannot highlight how important it is for you to minimize, again, compliance. Why? Because if you have the anti-roll bar attachment over here that is not stiff enough, or this attachment is going to, or it's being attached to the middle of a chassis tube, you might have the chassis tube twisting and decreasing the effectiveness of your anti-roll bar, meaning that whatever roll rate you designed for the anti-roll bar will be a lot lower because of this deflection, since you are adding another spring series. Just like in the case of the rocker system, here we're going to start by analyzing the anti-roll bar motion ratio. There are many different motion ratio definitions for the anti-roll bar. The one we are using here, it is basically car roll divided by anti-roll bar twist. This is the equivalent of the motion ratio we use in terms of wheel displacement versus damper displacement. We can see that in this case, we are finding a number of 0.07 over here. This means that as the car is rolling, the anti-roll bar is twisting a lot, which we have to be careful not to even break the anti-roll bar. So let's look at the target that we defined initially, and then we're going to get back to changing it. We can see that in our documentation, we defined the target anti-roll bar motion ratio of 0.1. Again, just for the sake of exercise. But in real life, how do you define and determine the motion ratio that you need for this system? Well, one thing you have to be careful is the following. If you have a very aggressive motion ratio, let's say that the car is rolling 1 or 2 degrees for a GT3 car, your anti-roll bar could be twisting a lot to the point that you break it. So it is very valid to run an analysis or even preliminary structural simulations in order to understand if with that given motion ratio you're targeting, if your anti-roll bars will not break. If we go back to OptimumKinematics, now we have to change our pickup points, again with this manual iteration and after with optimization, in order to get to this 0.1. So basically here, we need the anti-roll bar, we need to increase this number, meaning that the anti-roll bar will rotate less. We have two ways of doing that again. Number one is for a given rocker movement over here, we want the anti-roll bar being displaced less. And how do we do that? By decreasing the length of this arm over here. So we can take this pickup point and send it a little bit closer. So let's try this first approach first. In this case, we got a number slightly higher, close to 0.8. So we are still not at the 0.1. And the second approach we could take is to change the length of the blade. This could be done either by changing this pickup point or this other pickup point here. So if we increase the length of the blade, for the same linear movement on the upper pickup point, the anti-roll bar will rotate less. So let's try to change this pickup point and see what happens. Alright, so we are getting a lot closer to 0.1. I lowered this pickup point, the blade got longer, and then we increased the motion ratio. So I can keep running iterations to see where we get, but since later we're gonna use the optimization, I'm gonna say that I'm happy with this. Before we move forward, there is something extremely important. Just like all the other pickup points on the rocker should be on the same plane so that you don't introduce twisting moments on the rocker, you should have the same consideration for the anti-roll bar. Remember that there will be a force coming from the droop link to the rocker, and if it's too out of plane, it's gonna make the rocker twist and bend. So we should be taking that into account. So in this case, we can see that we are not too far off from the plane. At least typically the forces are smaller than the springs, so you do have a little bit of more tolerance over there, but you should keep that in mind. So you might have to adjust this point up and down or even to the sides in order to keep the droop link on the same plane as the rocker. The second consideration is the following. Not only you have to think about this plane, you also have to think about the blade. Because if the forces from the droop link are too out of plane with the blade, let's say that over here we would have a droop link in a completely opposite direction, not only you are twisting the anti-roll bar normally, you are also creating some flexion and some deformation on the blade. So you have to be mindful of that as well. Now that we are relatively done with the static motion ratio, we are going to go for the motion ratio variation. Again, sometimes even more important than the static number, is the variation that we get. For that, I'll run a heave simulation to understand at different vehicle heights, how are we changing the entry-roll bar motion ratio. And now with the results ready, we can plot them. This is what we got. As we know, the initial number was close to 0.95 for the static position, even though later on we want to bring it closer to 0.1 so that our entry bar is not twisting as much. But the second thing is we need to look at the variation. Again, we see a really high variation, which is normal. If you were not thinking about variation when designing the system, it's normal that you're going to get such a high variation. In this case, at least, so we are getting to a smaller number. So the number is going smaller and smaller, meaning that we are increasing the stiffness, the roll stiffness of the suspension as the car lowers. So in this case, at least, we're inducing some understeer for high-speed corners. However, in this case, it's way too much. In this case, the car would get too much mechanical understeering at high-speed corners. So what I would like to achieve here is not really to change the direction of the variation. However, I want to decrease the intensity of the variation. How do we do that? Well, first, let's define our target. In the same way as the spring, we can define how much roll stiffness variation we want for every 10 millimeters of car deflection. And once we know that, this will be proportional to motion ratio squared variation. Just like in the case of the rocker, the motion ratio variation is all about the angles. So the angle of the droop link versus the rocker, or even more importantly, the angle of the droop link versus the blade will heavily dictate the motion ratio variation you have. So let's try to look from a side view, and we can see that we have the entry bar down here, we have the blade, and we have the droop link. In this case, the blade has a very high angle compared to the droop link, which will typically induce more variation. Let's try to decrease that. Let's try to have something closer to 90 degrees. And then from 90 degrees, we can move a little bit backward or forward in order to determine the direction of the variation. In this case, I'll simply send this point a little bit forward and then get this angle closer to 90 degrees. Now with the angle closer to 90 degrees, I'm going to run another simulation to see where we are. These are the results we got now in green. We can see that the motion ratio changed a little bit, which is normal. We are changing the parameters. It actually got closer to 0.1, which is what we want. But on top of that, just look how much the variation of motion ratio changed. Now we have maybe 3 or 4 times less variation than what we had before. And then we can look if for 10 millimeters of wheel displacement, if we are getting the variation that we wanted. Actually, we're pretty close. We're changing 0.001, 0.0015, which is more or less what we wanted. So we see that by running a manual iteration, we got closer to what we wanted. But in any case, we would have to run a couple more iterations to get to the exact shape of the curve that we would like, as well as to the static motion ratio of 0.1 that we would like to see. So now that we're happy with the entry bar motion ratio and motion ratio variation versus heave, there is one last topic for us to discuss about entry bar, which are entry bar adjustments. So entry bars are a very powerful tool at the track for you to change the mechanical balance of the car. And how do you do that? You change something on the stiffness of the system that will influence the roll stiffness of that axle, which will then change vehicle balance. In this example, we could have different options. We could have the blade being a flexible blade where you just adjust the angle and it changes the stiffness of the component. Or what we're going to use for this case, since it's just a little simpler, we're going to define different pickup points over here. So when we look at the blade, we would have different attachment points a little further away or a little closer to the entry bar, and this will change the stiffness of the system. So if we have pickup points a little closer to the entry bar, for the same suspension movement, the entry bar will twist more, meaning that you make your entry bar effectively more stiff. And if you make this pickup point a little further away, you're going to get a softer entry bar from that. So in our case, what we want, again, we don't want to simply find pickup points at 10 or 20 millimeter steps. We want to define first, as always, what the targets that we're trying to achieve are, and then how much adjustment we need on the entry bar to get to that. So we could be thinking, what is the range of mechanical balance adjustment that we want? Or if we want to be more specific, what is the roll stiffness variation that we want from the entry bars from the different pickup points? Now, I would say I'm pretty happy with entry bar motion ratio and entry bar motion ratio variation. We also determined different entry bar adjustments And the only thing missing is for us now to iterate and then get to the exact values that we had in mind when we defined the design target. For that, instead of keep doing manual iterations, which are very time consuming, we have two different options. Either you could have a parameterized CAD model that we have discussed in previous episodes to help you with the design, or we should be running optimizations, which is what we're gonna do right now. So I already have an optimization setup where we're gonna define or indicate what pickup points the solver can play with, what pickup points he can change in order to achieve the objectives that we would like. And I also defined the objectives. In this case, since we are designing the actuation systems, I defined a few different parameters. Number one is the motion ratio in heave, as well as the motion ratio variation, basically the green line, how it is changing as we compress the suspension. And I also defined the same for the entry bar. What is the static motion ratio for the entry bar, and what is the motion ratio variation that we want to achieve. Besides that, it is also very important, and OptimumKinematics is powerful because it allows us to do that, is for you to make sure that all of the components are still on the same plane and aligned. And you can do that by ensuring that the angle between the rocker and the coilover is close to 0, meaning that they are aligned. As you can see here, the target is 0, but also that the angle between the push rod and the rocker is also close to 0. And remember, it's not only about the static position, it's for the whole stroke of the suspension movement. We need to make sure that these angles are not critical, they are close to 0. We can then run this optimization and see what we can find. So an optimization will be very powerful because it will find the best compromise between all the different objectives that we just defined. So let's run the simulation. Once we start it, you're going to see that it will be finding different pickup points that optimize to the objectives that we're defining. So you can see that each generation will find a best or a new best suspension. We're going to leave that running for a few iterations, and then we're going to be able to look at what objectives the optimization was able to achieve. So after running about 100 generations, let's see how the optimization module in OptimumKinematics performed. First, let's look at the objectives. So we defined the motion ratio and motion ratio variation that we would like as seen in green, which is our objectives, and we see in blue what the optimization was able to find. So it's trying to look at many different compromises at the same time in terms of angles, static motion ratio variation. And we can see that it got up to a pretty good result. So the static motion ratio is off by only about 0.01, and the motion variation is pretty much what we wanted in compression. As I mentioned, it's normal that we have a little bit of a sine shape when dealing with rockers, so this is common. Now, if we go to the motion ratio of the entry bar, this is what we get. We had the objective in green with 0.1 defined as target, and the optimizer, looking at everything at the same time, found 0.102, which is really close to what we wanted, as well as a variation close to what we wanted. So we can see that the general shape is following what we defined. We can also see that the coilover angle versus the rocker was completely minimized for the entire range of suspension movement. And we can also look at the push rod angle versus the rocker, which was also minimized. In this case, it is not possible to achieve 0 since you have suspension movement. However, you can see that it tries to keep it as close to 0 as possible. So I would say that we're happy with the results that we got. We can now investigate and understand if all of the components make sense and we don't have any conflicts between different components. We have the V9. I want to now run simulations and see how it performs versus the initial manual iterations we've done. Now we can look at the final results. So here we are looking at the motion ratio for the coilover, and in red we have the last version. So we started with the version in blue with lots of variation, and then we were trying to get the motion ratio variation right with the yellow and orange lines. We were getting there, but then the motion ratio static was changing. Now we can see that with the result, the final result we got with V9, we have the static motion ratio we would like to have, as well as the motion ratio variation. If we go for the anti-roll bar plots, again, we started in purple. We tried to decrease the variation, which we did successfully, even though the static motion ratio was still wrong. And now with V9, we have all of them correct. So we have the static motion ratio we want, as well as the variation. And as we saw with the angles, all of the angles are minimized. all the pickup points are on the same plane, and I'll say that we successfully designed the rocker and anti-roll bar systems that we wanted. In this episode, we went from no actuation system at all. We designed our initial draft with many considerations in terms of compliances. Then we understood the two main parameters we should be looking at, motion ratio and motion ratio variation. We discussed how to achieve each of them, how to get to the motion ratio you want and to the variation we want, and also we repeated the same process for the anti-roll bar system. Now you should have most of the tools that you need to design your own actuation systems and get to ideal car performance. If you like this content, I think you'll be really interested in our seminars. We have our Vehicle Dynamics seminar where we're going to discuss in a lot more depth the whole process of suspension design, including not only kinematics, but also stiffness, damping, and car performance. Besides that, we have our Performance Engineering seminar where we're going to discuss many different data analysis techniques and performance methodologies to make your car the fastest at the track. You can find the link to the seminar calendar in the video description. And these are the services that we offer. Vehicle Dynamics Consulting, where we could be helping you design your race car or your passenger car suspension, besides many other services such as vehicle testing, development, or simulation. We also offer performance engineering, where you could have one of our performance engineers at the track with you, applying all the methodologies that we use. And we also sell simulation software in the areas of kinematics modeling with OptimumKinematics, as well as tire modeling and vehicle dynamics. You can find a lot more about that on our website. Thank you for watching. If you have any questions, please leave them in the comment section so that I can get back to you, and I'll see you in the next one.